We have constructed a board where we have mounted loads from each category: fixed load, curtailable load, shiftable load, and controllable load. These loads are interfaced with the microcontroller through relays and sensors. In order to control these loads in a smart fashion, we have designed a mobile application so you can control these loads through these buttons on the phone. It also shows you your current power consumption in form of digits as well as the graph, and also the tariff rate at the moment. You can also use Google Assistant to control these devices through voice. Turn on outdoor lights.
Okay, switching on outdoor lights.
Turn off outdoor lights.
Okay, switching off outdoor lights.
The microcontroller takes in data from sensors and calculates the power. Now, these power details are sent on to a server via the internet, and they can be represented onto this website. Now, this website mimics our utility. Here you can see the power consumption details getting updated, and this data can be extracted in form of an Excel sheet. Now, here you can see the time and the power consumption beside it. This can be used to calculate the consumer bill in a remote manner. To assist utility to find time of use rates, we have taken 2 days data from IEX platform. Here it is in the form of a graph. This data is then sent over to a Python script where it is averaged and normalized. This is the end result. The curve can be made smooth to get a time of use tariff structure. The final red graph is then used in load shifting and optimizing algorithms. Considering this time of use curve, if you were to use your washing machine in this time slot, you would not only incur expensive bill, but you would also stress the utility at peak hours. Now to solve this, you can shift this washing machine to another period where it is less expensive. So if I turn on my washing machine in a peak period, I would get a notification stating to shift it. To shift, I can press the shift button or use Google Assistant. Shift washing machine.
Okay, washing machine has been shifted.
For the water heater setup, we have a bucket. Inside that we have a water heater and a temperature sensor. Both are connected to their respective circuitry. My water heater is turned on. As you can see, the power consumption is just shoot up. And what you can see here is the actual temperature and desired temperature. Now, actual temperature is what is the temperature inside the bucket, the temperature of the water, and the desired temperature is how much I want the water to be heated up to. The thing about controlling the water heater is that I can vary the desired temperature. As you can see, there's a slider here. So if I vary the slider, I can actually increase the water heater temperature to 41 degrees Celsius. Now if I want to increase it more, if I go maximum, then 45 degrees Celsius is the desired temperature. As soon as actual temperature is reached, the water heater switch is turned off and you can see that the power consumption is then again reduced to the fixed load consumption. We know that for more cooling, the AC consumes more power. This algorithm is divided into two parts. In the first part, based upon the room temperature, that is how hot the room is, we find an AC set temperature. This set temperature will give the consumer cooling. In the second part, since we have taken time of use rates, we have to ensure lower AC energy consumption in the peak hours. To achieve this, AC temperature should be mapped with time of use rates such that that temperature would give you lesser power consumption. Now, we have two temperatures, one that gives you cooling, one that gives you energy saving. By taking a weighted average of both, we can find a final temperature which gives you cooling along with bill savings.